All right. Any questions at all about anything going on in the class? I just posted solutions for homework 5. I apologize. I completely forgot to do that on Friday, but hopefully it gives you enough time to look it over. Exam is on Thursday night. Office hours this week are basically the same as they are every week, except tonight, Zhao is going to have prepared content for review session. And then on Tuesday, it's going to be sort of an open question free for all with both Zhao and Jonathan there. They'll maybe figure out something with breakout rooms or whatever, or just, whatever is convenient for all of you guys. And then I will also have my typical after class office hour session on Wednesdays. Okay.
Will the previous will previous versions of like the exams be uploaded on Canvas for practice? Or
Yeah, I'll see what I can do. I can try and give you a few practice problems. I know that during the review sessions and stuff, they will also have different practice problems that they can go over and stuff like that.
Okay, thank you.
And then I'll send out like announcements with like instructions for how to do for how to actually do the exam and stuff like that, and we can discuss a little bit on Wednesday as well on how to submit the exam and stuff, right? So.
I had one other question for
Yeah.
the index notation. There was that file uploaded with just like, summary of all the important points, and there's some problems at the end. A lot of them are just proofs, so I guess like you'd know if you did it right. But are there solutions to those problems just to make sure you're like getting those right, or is nothing?
I actually don't know. I'd have to look. I don't know off the top of my head. It might be a sort of thing where if there are things that you're confused about, just come find me on during office hours or something like that. That might be the easiest, but I don't remember. I might have it somewhere. I'm not sure.
Okay, cool. Thank you.
Mm-hmm. Any other questions? Okay, so like I said, this is all sort of beyond exam material that we're covering at this point. I have not started sharing my screen, have I? Let me do that. Sharing this. So we've been talking about these this case of what we call nearly unidirectional flow, where we have basically something that's flowing inside, let's say in this particular case. So we'll do an example where that looks a little bit different than this, but sort of the general case is like we could have potentially a two-dimensional flow here. So now we care about both Vx and Vy in this case. And Vx and Vy could vary with both x and y, and so the solution could be potentially complicated, right? We have a partial differential equation or a system of partial differential equations. Vx and Vy could depend on both x and y, for instance, right? But by doing some scaling beforehand of the various terms in the Navier-Stokes equation, we're able to show that certain terms matter a lot more than others. And that then allows us to figure out how to actually solve these equations in a more approximate sense, right? So for instance, the complicated Navier-Stokes equations then reduce down to something that's fairly simple and looks pretty familiar to what you guys have seen. And then we apply this to basically just a typical pressure-driven flow problem, except the channel can have a varying width of some arbitrary h of x here, right? That allowed us to get a solution, and as we expected, the solution is we have a Vx and a Vy, and they both actually do vary with both y and h here, and h of course varies with x. So Vx is a function of both x and y, right? And yet we were able to kind of get away with not having to really solve a partial differential equation because of the way that we were able to do some approximations, basically, right? These approximations only worked when, for instance, we said the Reynolds number was small enough, or and when the thickness of the channel is small compared to the length of the channel, or something like that, right? So today I'm going to do just one more quick example on how these things work. And so the example is now instead of a channel of varying width, we're going to do flow in a tube with a slightly permeable wall. Okay, let me just draw a little picture to explain what I mean when I say that. Sorry, I'm adjusting my hardware here. So let's say I have a tube here. And like we would normally do, you have a fluid coming in at some average velocity u0. This tube has a length of L and has a radius of R. So this length is therefore 2R. And what's a little special about this tube is that it's, as I mentioned, it's slightly permeable. And so there could potentially be fluid going out of the wall at some velocity, VW, V wall, or something like that. Okay. And so, without this VW, if this VW here would be 0, then we've done this problem before. You've done this problem in undergrad. You could do this problem in your sleep, right? It's really, really simple. The problem is that now, because we have this VW, you could imagine then that both VR and VZ are going to be functions of R and Z, right? Before, we always had VZ is just a function of R, right? We saw that VZ is some parabolic flow profile, right? Now here we're going to have a VR by definition because our VW here is not 0, so there's going to be some flow in the R direction, right? And you could imagine then that the flow profile could change as you move down the tube, right? And so how are we going to analyze this? We can use a similar sort of scaling argument to try and simplify the Navier-Stokes equations to, again, cheat and get away with not having to solve a full partial differential equation system here, okay? Now, as I mentioned, the reason why we have to do this is because there are axial variations. And these variations are caused by the slow fluid loss through the wall. Okay. The way that we're going to be able to simplify the Navier-Stokes equation stuff is we use a similar assumption as we were doing earlier in the gradually varying channel. We're going to assume that VW is much, much less than U0. Okay, so it's a slightly permeable wall, right? And so now we need to ask ourselves basically, when does this stuff, like, how do the axial variations actually matter, basically, right? Or another way of saying this is over what length scale does VZ vary, right? And so we can do similar scaling arguments as what we've done so far, like in the previous problem, okay? So let's do some scaling here. What these scaling arguments really are talking about is basically, for instance, when I say that VZ scales as U0, that's what you guys might expect, right? What that means is that the maximum variation in our problem of VZ, if I had to take a derivative in our problem, what's the maximum possible what's the maximum possible change in VZ over our problem? Well, that's going to be U0 because VZ should go from either U0 down to 0 somewhere else, right? Likewise, VR should scale as something like VW here, right? And R, basically any derivative with respect to R should have a denominator of something like big R, the radius here, right? Now, the length scale for Z here is actually not L. It's actually some length scale LZ, and it's unknown here what this length scale is. I know that when we stare at this problem, the first thing you might think is, oh, this length scale is actually just going to be L, right? But this length scale should actually be controlled by the physics of the problem, not by what's actually given by the problem. Because you could imagine if, for instance, VW is too large, then the flow initially U0 over here would actually stop to 0 at some point before you even reach the end of the tube here, right? And this LZ is basically, again, our question is over what length scale does VZ vary? For instance, how long does it take as we move down the tube for VZ to vary from U0 all the way down to 0? We don't know what that is, but we need to assign it some length scale that isn't necessarily the length of the tube itself. I forgot up here to give us axes here, but hopefully that was pretty clear what I was going to do here.
So we could say that Z scales with L if there was like a boundary condition at L though.
Sure. Yeah. Something like that.
Also, real quick, how is VR different from VW?
What do you mean?
Like, does VW vary with radius? Is it constant? Is that an assumption
VW
we're
is just
making?
VW is just a constant. It's the flow. It's the velocity of the fluid at the surface of the tube, basically. But that's not necessarily going to be the like VR varies as R and Z, right? VR is a function of R and Z. It's the flow profile inside the actual tube, and so you can't say that it's the same as VW because VW only tells you what it is at the surface. Does that make sense? Okay. And so just like before, we can do all of our scaling analysis here and then maybe learn a little bit about how the different terms in the Navier-Stokes equation depend on one another, right? And so the easiest thing that we typically do is we first deal with the continuity equation. If I can spell continuity. Okay, the continuity equation in cylindrical coordinates looks like this. Okay. And so what this implies then is that, well, this first term should scale as something like VW over R, right? You multiply it once by R, but then you divide by R because you took a derivative, and then you divide by it again because it's over R. So that's what the first term should scale as. And that should therefore scale as the second term, which the second term scales as U0 over LZ, right? And so what that implies then is that LZ actually scales as R over U0 over VW. Okay. And what that implies is, of course, we assumed earlier that U0 is much, much greater than VW. It's a slightly permeable wall. And so because U0 is much, much greater than VW, then LZ is much, much greater than R. Okay. So what this means is that the axial variation is gradual. For VR and VZ. Sorry, my handwriting's terrible today. And VZ. Okay. Okay. Just like before, we can also look at the other components of the Navier-Stokes equation. So for instance, let's look at the Z component. Here's what the Z component of the Navier-Stokes equation looks like. I'm omitting the theta component, V theta here. I should have said that explicitly, but hopefully that's pretty apparent from what's going on here. Okay, and just like before, we can figure out how each of these terms should scale based on the different parameters that would be given in our problem. Okay, so the first term would look something like this. We have a rho here. So let me put down our rho. And then VR scales as VW. VZ scales as U0. And then, of course, we have an R on the bottom here, right? The second term is just going to be rho times VZ, so that's just U0 squared. And then Z scales as LZ, so LZ. Okay. Let's not worry about dP dZ for a second. This term right here should scale as mu times U0 over R squared, because VZ scales as U0, and then little r scales as big R. And there's two derivatives of that, basically. And the second term should scale as mu times u0 over LZ squared. Okay. And so we've seen this before, so I'm not going to go through all the different steps. But this first step, so I won't go through them in all the different in all the same detail that we did on Friday. But you know, you can simplify this one right here because you know how VW should scale. VW, according to this up here, should scale as R times U0 over LZ. Okay, and so therefore this first term actually looks like this. Second term stays the same. You can see that the two inertial terms scale similarly, right? This term over here is the same. And this term we're not going to worry too much about because LZ is much, much greater than R. And so therefore this term is much smaller, right? Okay. Okay, and just like before, we can compare how the inertial terms actually would actually compare to the viscous terms. And so again, we can look at the ratio of the inertial terms to the viscous terms. And that gives us something like rho u0 r over mu times r over LZ. And that's after, you know, a little bit of simplification. Basically, I cancel this u0. I cancel this u0 squared with a u0 on the bottom when I take that quotient. Okay, and so this is basically, you guys recognize this just like before. This is a Reynolds number. Okay, times r over LZ. Okay, or another way of writing this, an equally valid way of writing this is a Reynolds number times VW over u0. Right. And so again, what this implies then is that if this quantity here, Reynolds number times VW over u0 is much, much less than 1, then we can ignore the inertial terms and only care about the viscous terms in our Navier-Stokes equation here, right? As I mentioned, I'll skip a few steps because I could basically do the same thing for the R component of the Navier-Stokes equation, but you guys will get very, very quickly bored by that because the analysis is very similar to what we've shown here and what we did on Friday. So I'm going to go ahead and skip that. But I'll summarize what all the scaling implies. This means that if, say thus, if VW is much, much less than U0, and the Reynolds number times VW over U0 is much, much less than 1, then the Navier-Stokes equations reduce down to this. Okay, there's that. And then pressure is only a function of Z only. Okay. And these are basically the same equations as what we dealt with earlier on Friday. And so for the rest of this class, for the rest of this lecture, I'm just going to actually, you know, solve this equation for this particular example, and then find different flow profiles and how pressure varies and stuff like that. Any questions at this point?
Why did we get rid of any R functional dependence over pressure?
Oh, it's analogous to the to what we did on Friday. To do that, I would have to go in and here, I'll try and show you this real quick from Friday, just to jog your memory for a second. From Friday, we looked at the Y component of Navier-Stokes. In this case, it would be analogous to the R component right here, right? And then we calculated, and then we showed that, you know, so under similar conditions, we can ignore the inertial terms according to the viscous terms. That gives us different scales for what the pressure term is going to look like. The pressure term has to scale as this from the X component, and the pressure term has to scale as this from the Y component. And then we found, therefore, that the pressure variation in Y is much, much less than the pressure variation in X. Similar idea here. Okay, and I'll encourage you to go home and sort of play with that yourself. The analysis looks essentially identical, which is why I'm not spending time on it right now.
Okay, thank you.
Okay. Okay. And so now we just need to basically solve this. And so again, let me just take a quick step back, and then maybe we can gain a little bit of appreciation for what happened here. As we opened the class today talking about this, we noticed that basically VR and VZ both have to be functions of R and Z, right? And so that might imply that you have to solve a PDE in order to actually get these, to get the solution here. But we were able to take our Navier-Stokes equation, which was kind of complicated right here, and then reduce it down to something that's just an ODE at this point. And we should be able to solve fairly easily. Okay. Now we have to be a little bit careful. We have to worry about like mass conservation and stuff like that, just like we did earlier. We have to worry about the fact that our dPdz could potentially be changing along Z and stuff like that. But that's okay. We just have to take all that into account in our analysis. Okay. And so now basically, let's go ahead and solve the ODE. Okay. If I can write. So let's solve the ODE. The way we're going to do this is, again, I'm going to skip a few steps because you guys have seen this so many times already. But basically, we just integrate twice. Okay, and then we apply the boundary conditions that I've been too lazy to write at r equals 0 and r equals r. Right? Those boundary conditions, just so you know, it's that r remains finite that vz remains finite at r equals 0. And then that vz is equal to 0 at r equals r, right? The no-slip boundary condition and then the symmetry condition, right? You guys have seen this so many times. You guys have done the pipe flow problem, like I said, and so that's why I'm being a little lazy here, right? What we get then is a solution that looks like this. Okay, you'll see that basically this looks identical to the pipe flow problem solution, right? And that's why I'm not showing you guys the solution, because you've seen this already so many times. The problem is we're not quite done yet because we're not actually given what dPdz is. And in the pipe flow problem, we know that dPdz is just, the pressure drop divided by the length of the tube, right? But in this case, we have a permeable wall, and we potentially have axial variation, so variation along the axis of the tube, right? And so dPdz can potentially vary with Z, right? So I'll just say we are not done yet. Okay. This is because dPdz can vary with Z. So if you remember a little bit from the lecture on Friday, the way that we calculated how dPdz varies with Z is we actually looked at the overall flow rate of the fluid through the tube. And then we did some sort of balance. We did some sort of mass conservation argument, right? That's how we figured that out. We can basically do the same thing here. Instead of doing flow rate, today I'll just do mean velocity. It's sort of the same thing. So I'll say look at.
Could we do it with flow rate here? Or
You could. It'll look exactly the same. I'll just show you, I'll show you with mean velocity, and then all you have to do is multiply by pi r squared, and you get flow rate. So it's basically the same thing. All right. So let's look at mean velocity. I'll call that little u here. That's, as I mentioned to Eric's question, that's just flow rate divided by pi r squared. Okay. And so to calculate that, what I'm going to do is take this velocity and do an integral, do a surface integral at some constant value of z. Okay. And so what I get is 1 over pi r squared times the integral from 0 to r of vz times 2 pi r dr. Excuse me. And so I get I'm just plugging in my definition or my solution for vz. And then I just need to integrate this. Okay, this is a fairly simple integral. Cancel this. We'll cancel this 2 pi over here with this 4 pi over here. So I'm left with -1 over 2 mu r squared. Oh, sorry, I forgot to put in my dp dz here. Let me see if I can move this guy and then write a dp dz. Okay. I'm left with this times dp dz. Okay, and then I just need to integrate whatever's in here. So I get okay. And that gives me that u of z is equal to okay. And if you look at the solution for in pipe flow, this is exactly identical. Okay. And so what this implies then is that dp dz is equal to negative 8 mu over r squared times u of z. And so then I can plug in this dp dz up here. And then I get that therefore vz as a function of r and z is equal to 2 times u of z 1 minus r over big R squared. Okay. To calculate our mean velocity, or as if you prefer, our flow rate, remember this flow rate could potentially change with respect to z, right? And so to calculate that, we can use a macroscopic balance, kind of like how before we could we were using something like mass conservation. We can basically do the same thing here. Okay. So we can use a macroscopic balance to find u of z. The way we're going to do that is, here's our pipe again, let's say. I cannot draw a straight line, sorry. Still can't draw a straight line, okay. There's that. As always, we have some fluid coming in at an average velocity of u0 initially, at a position of z equals 0. If we have some arbitrary position z somewhere, and we want to know what is the flow rate or what's the average flow rate at this position z right here, then I could maybe just draw myself a little control volume, like so. Like that. You guys can see that control volume, hopefully. Okay. And of course, the average flow rate coming out of this control volume right here is going to be u of z as what we want, right? And then of course, there's also going to be some amount of flow coming out of the control volume through the sides, and that has a velocity of vw, right? So the macroscopic balance, basically in minus out, is equal to 0, or in equals out. In is u0 times pi radius squared. Okay, and then coming out on the right-hand side, we have u of z times pi radius squared. Okay, and then through the sides, we have vw times the surface area of that cylinder on the sides, right? So 2 pi r is just the circumference of the circle times z. Okay, and so what this implies then is that u of z is just u0 minus 2vw z over r. And that gives us our solution in terms of what we're given in the problem, right? We're given in the problem like an initial u0 and a flow of the fluid through the wall here, right? And in our actual solution, we have basically you have to plug in this u of z right here, right? And our final solution, we get vz as a function of r and z is just equal to 2 times u0 minus 2vwz over r times 1 minus r over r squared. That. So do you guys kind of see how this is cheating, right? Like in an actual flow profile like this, if we did not have the assumption that VW is much, much less than U0, for instance, right? Might be way more complicated than this, right? You might not have a parabolic velocity profile in R, and you might not have something linearly related. Like you could have like crazy eddies going on. You could imagine if U0 were a similar order of magnitude of this, then the flow might look something more like this or something, right? Rather than this really nice velocity profile, which looks more like, this might be at the end. What we're saying that our velocity profile right now looks like is this. So initially, we have this nice parabolic velocity profile. And all we're saying is that as we progress through the tube, this parabola gets smaller and smaller. That's all we're basically saying, right? And that seems almost as if it's cheating, right? You're just taking something that we already know, and then we're just like doing a very slight modification to that. But all this works because we're assuming that VW is much, much less than U0. Okay. Now, of course, once we get all the way over here, when the flow in the z direction starts to become really small, right? Then our approximation breaks down. Then our flow profile could actually look pretty different than what we would expect, right? What we're saying here is that basically most of the velocity is in the z direction, and it basically just always looks parabolic. What if, for instance, we keep going over here, then eventually maybe we'll start to actually get a flow profile that looks more like this, right? And then somewhere in the middle, I don't know what will happen. Maybe the flow will actually look more like this. That's what I was attempting to draw earlier. Okay, and so this looks nothing like a parabolic profile at all anymore, right? And that's my point, is that our assumptions initially are what really make the difference here, right? Basically, if we ask ourselves, like, what if UZ becomes negative? And that could easily happen, right? That would happen when we are at a Z position that's greater than our length scale LZ here, right? And if so basically our tube gets so long that we're starting to actually lose, we're starting to get the flow all the way down to 0 then, right? We can't, basically the answer is basically then we have to do a much more complicated analysis, and our really simple analysis here with a pretty simple solution, to be honest, is no longer going to be valid. Okay. So what that means is that our solution fails. We must keep the overall length of much, much less than that. Notice how this is basically LZ, right? It's a factor of 2, but when we're dealing with scaling, we don't worry about these order 1 constants and stuff. This is basically LZ, right? As we set up here, LZ is R times U0 over VW, right? U0 times R over VW right here. Okay, and when L equals this, when Z equals this, basically, then this term right here, U of Z just becomes 0, right? So we must keep the overall length to be smaller than this to preserve the nearly unidirectional flow approximation. Okay, does that kind of make sense? To dot our I's and cross our T's, let's go ahead and figure out what the other components of this, this flow profile might look like. For instance, this is VZ. We might also care about VR. Someone asked earlier, I think Kevin asked about what VR would actually look like and why it's different than VW. Well, we can do that. We can actually calculate what VR would be, right? So let's go ahead and do that. So we'll say find VR. And to do that, the easiest thing to do is just to use the continuity equation, because we already have VZ, and that's a pretty simple differential equation that we just have to solve to figure out what VR would be. Okay. Okay, so the continuity equation, as I wrote earlier, but I'll rewrite it here. That looks like this. Okay. And of course, we know what VZ is. That's this up here, right? And so then we can just plug that right in and then solve our differential equation. Okay, so we get -2 times this guy right here, derivative with respect to z, right? And so that's -2 VW over R times that. Okay. So I'm just going to multiply both sides by an R here to get that. This gives me 4 VW over R times R minus R cubed over R squared. Integrate once. Here, I'll write this in a little bit neater format. Plus some integration constant, right? And so then we get that VR is just equal to, I'll simplify here very quickly. That I just divided everything by little r. Okay. We can apply a boundary condition that VR is finite at r equals 0. That implies then that my C1 has to equal 0. And so then we're done. We get that VR as a function of R and Z is just equal to what I wrote down up here. Okay. And you might note that the other boundary condition that we might have for VR is also satisfied, right? We have one boundary condition that I wrote out here is that VR has to be equal to R equals 0, or has to be finite at R equals 0, right? The other boundary condition from our original problem is that VR might have to equal VW at R equals big R, right? And maybe you can plug that in right here and convince yourself that that is also satisfied. If little r is equal to big R, this gives me a 1 minus 1/2 times 2 is 1 is equal to VW, right? So I'll note that this is also satisfied. And the reason is just because it's a similar idea as what we had before. We basically used a macroscopic balance. And so this already takes this conservation of mass idea into account. Okay. You can also look at the pressure drop, for instance. That's another thing that one might commonly ask about. So to do that, we calculated what dp dz is. That's right here. And we know what u of z is from this macroscopic balance. And so we just have to integrate once, and then we can calculate what pressure is going to be. Okay. So what that means then is dp dz is equal to minus 8 mu over r squared times u of z. That's what we wrote earlier. We figured out what our u of z is. Okay. And then we can integrate to calculate what the pressure would be at the inlet and the outlet of our tube here, right? So for instance, that is just minus the integral dp, which is equal to this other integral over here. Oops, sorry. Yeah, I basically just multiplied both sides of this equation by dz and it integrated from z equals 0 to z equals L. Okay, and so I get okay. You can see that unlike before, or sorry, unlike the typical pipe flow problem, where the pressure drop varies linearly with L, here we actually have that varies quadratically with L, right? There's an L here and then an L and then another L right here. So the two are multiplied together. It's L squared. Okay. Any questions at all about this example? All right. I'm going to do just one more very, very quick scaling example. I think I only have like 10 minutes left or something. Okay. One way that the nearly unidirectional flow problem is typically taught, or another way of calling it, is people like to call it the lubrication approximation. So let me actually look at that in a little bit more detail here. So if we have, let's say, a floor or something, and we have some object that's sitting on top of it, okay, with some amount of fluid in between right here. So there's some sort of fluid here, okay? What we're dealing with in lubrication is, let's say that this object is moving across this surface. So it's all motion is all relative. So let's just say that the floor is moving in this direction with a speed of u. Okay. Then what we're basically asking is, in a lubrication problem, is how much force does this fluid exert onto this object right here in both the x direction here and in the y direction here, right? Because you can imagine this is the force that if this object were moving towards the left here, or again if the floor is moving to the right, this Fx might be something like a drag force, right? That would be the force that resists you from being able to push this object across the ground, right? This Fy would be like a normal force. It would be the amount of force that actually supports this object sitting on top of the fluid, right? And the question that we're asking in lubrication is basically, what's the relative values of these two forces right here, right? Well, we don't in general need to actually calculate the flow profile of the fluid here. We can actually answer this question just by looking at scaling. Okay. From what we've seen so far, we always end up with an OD that looks something like this. Sometimes we write it as d squared Vx dy squared equals 1 over mu dp dx, but same thing, right? And so what this means is that we would have some sort of pressure scale So how pressure changes as we look at this. Remember, typically what we see is that the pressure only is a function of x, and that pressure could change anywhere between ambient pressure all the way out here to some maybe higher pressure in the middle here. Okay, that pressure should scale as something like this. Okay, sorry, I guess I should draw some dimensions here. There's some sort of length here. And then there's some sort of thickness of the fluid layer here. Okay. Excuse me. Likewise, we can also calculate like the scale of shear stresses within our fluid here, right? You guys remember how to calculate shear stress, right? Shear stress is just Newton's law of viscosity. And Vx scales as U, and Y scales as H, just like up here, right? And so that implies that the shear stresses scale as So what this means then, we care about, again, two different forces that could potentially be exerted on this object, right? There's a normal force, right? That normal force is something like an Fy. And geometrically, that should scale as pressure times area, the area of this object that actually contacts the fluid, right? You could also think about a drag force, and that should scale as the shear stresses. Sorry, I should write f of x. F sub x should scale as the shear stresses times an area, right? Because again, the shear stresses is basically like how much shear, I guess, is the fluid actually exerting on that top surface, right? Whereas the normal force is how much pressure is the fluid pushing up against that top surface there, right? And so if what we care about is, let's say, what is our normal force compared to our drag force? So this is normal compared to drag, right? That should scale as pressure divided by tau. But we know how pressure scales. That's up here. Okay, so that's mu ul over h squared. And we know how tau scales as well. That's also up there. That's mu u over h. Okay. And you can maybe see how certain things are going to cancel each other out here, right? This is these mu's cancel, these u's cancel. One of the h's cancels, and what you're left with is L over h. And typically the assumption in these sorts of problems is that L is much, much greater than h, right? And so the conclusion here is that if L is much, much greater than h, then f of y, or f sub y, is much, much greater than f sub x. In words, what this means is that a thin layer of fluid can support a large load with a small drag between surfaces, right? And this is exactly how lubrication works. This is exactly why, you know, when you put a fluid in between two objects, that allows them to move past each other very, very easily, because the amount of force that's required to move them past each other is much, much less than the amount of fluid than the amount of force that's required to push them against each other. Picture like an ice skate on a layer of ice or something like that, right? Similar idea here. Okay. And I think it's kind of cool that without even actually having to solve for any sort of flow profile at all, you can just look at how these terms scale and then immediately arrive at this conclusion.
Mitchell?
Yeah.
Is this saying that the thinner the fluid layer is, does it imply anything about like the choice of H? Like,
yeah, it just means a very, like, the thinner the fluid, then the more it's going to lubricate, basically.
okay, thanks.
Yep, and that's so this is one reason why in the syllabus, for instance, this unit is called the lubrication approximation. People like to use that a lot because this is essentially the key result that people are able to use. Using these sorts of scaling arguments and stuff, you can immediately see that that, you know, this complicated Navier-Stokes stuff reduces down to something that's fairly simple and straightforward. And we can use, you know, our typical ODE solution techniques with maybe a little bit of a few different caveats to then understand what the flow profiles are going to be. Okay. All right, that was all I wanted to say today. If there are no more questions, I'll see you guys on Wednesday.
One question, sorry, I missed. How did we get the scale of the pressure term?
Yeah. So this is the ODE, right?
Yeah.
So dP dx, which scales as P over L, right, should scale as mu times Vx, which is U, scales as U, and then Y squared. And there's my son in the background.
Cool, yeah, makes sense.
See ya.